In this video, we will talk about how we can use Hess's law to determine the enthalpy of any reaction using the reactants and the products enthalpy of formation. This method is based on the concept that in any chemical equation, the reactants must firstly be dismantled into its elements. That is, it is a decomposition reaction. However, the products must then be put back together. This will be a formation reaction. And we've talked about the heats of formation as well as the heat of decompositions. So we'll use these enthalpies of formation and enthalpies of decomposition to calculate the enthalpy of our desired reaction. The example we're going to work through today is the reaction with calcium oxide with carbon dioxide to form calcium carbonate. We were asked to find the enthalpy of the reaction as well as the molar enthalpy of the reaction for calcium oxide. Before we start with the example, let's look at our balance equation. We have calcium oxide reacting with carbon dioxide to form calcium carbonate. Here the reaction is already balanced. Let's ask ourselves, what substance must be dismantled? And these are the reactants. We have to dismantle calcium oxide into its elements. So here we have the deformation reaction or the decomposition reaction. Notice here we balance oxygens using a fraction because we want to keep the coefficient for the carbon oxide to be 1. The other compound that we have to dismantle is carbon dioxide. And here is the deformation or the decomposition reaction for carbon dioxide. Next, we ask ourselves, what substance must be put together? And that must be the product, calcium carbonate. Here we have the formation reaction for calcium carbonate. Again, notice that we're using fractional coefficients because we want to keep the coefficient for calcium carbonate to be at 1. So if we add up all these reactions together, we should get the overall reaction back. And here we have the decomposition reactions for our reactants and the formation reaction for our product. We add them up and we see that yes, we do get back our original equation. Calcium oxide plus carbon dioxide yielding calcium carbonate. The next step we can do is we add up all the enthalpy of the reactions. Now because these are all either simple formation reactions or simple decomposition reactions, these molar enthalpies can be found in your data booklet. Here we have the decomposition reactions. So the values that we use here are the negatives of the formation enthalpy change that is found in your data booklet. As for calcium carbonate, we use the data value given to us in our data table as is because this is a formation reaction. Adding up all these enthalpies together, we get a final answer of negative 179.2 kilojoules. So if we put this into an equation, this will be the total enthalpy of the reaction. However, we're also asked to find the molar enthalpy for calcium oxide. And because the coefficient for calcium oxide is the invisible 1, we have to divide 179.2 kilojoules by 1 to find that the molar enthalpy for calcium oxide is also negative 179.2 kilojoules. Now that we've understood how we can use the enthalpy of formation and the enthalpy of decomposition to calculate the enthalpy change for any reaction, we can now come up with a shortcut method. The first step in our shortcut method is to look up all of the enthalpy values, enthalpy of formation values for all of our compounds, both reactants and products. And we'll write them underneath each of the compounds in our chemical equations. And we're not going to adjust the positive or negative values. The second step is to sum up, that is, to add all of the heats of formation values for the reactants on the left-hand side of the arrow, and then find the heat of formation for all the products. And then we will use, in the third step, this equation to determine the overall enthalpy of the reaction. Here we have the sigma symbol again, which means the sum of. N is the coefficient, the number of moles for each reactant or the product. The molar enthalpy of the products can be determined using your data table. So here we have the sum of the enthalpy of formation for all the products minus the sum of all the enthalpy of formation for all the reactants. This equation is not in your data sheet, but it is a useful formula to remember. Using the same example, let's try out this new shortcut method. From our data table, we look up the heats of formation for calcium oxide to be negative 634.9 kilojoules. The enthalpy of formation for carbon dioxide is negative 393.5 kilojoules. And the heat of formation, the enthalpy of formation for calcium carbonate is negative 1276.6 kilojoules. If we add up 634 with negative 393.5, we get negative 1028.4 kilojoules. And because there's only one product, the sum here stays the same on the product side. We can now use our shortcut equation. The sum of the heat of formation for our products is negative 1207.6 kilojoules minus the sum of all the heat of formation for our reactant, which is negative 1028.4 kilojoules. We do our math, and the answer here is negative 179.2 kilojoules. That is for each one equation. And we divide by the coefficient in front of calcium oxide, which is 1, to get the molar enthalpy of the reaction for calcium oxide to be negative 179.2 kilojoules per mole. Let's use our shortcut method to solve another example. Here we want to find the molar heat of reaction for the combustion of butane. The first thing we need to do, as always, is to come up with a balanced equation. 2 moles of butane will react with 13 moles of oxygen gas to produce 8 moles of carbon dioxide and 10 moles of gaseous water. The first thing we need to do is to look up the heat of formation for all of our reactants and all of our products. If we look up our heat of formation for butane, we find is negative 125.7 kilojoules. We have to multiply this number by 2 because the coefficient in our balanced equation is 2. For oxygen, because it is an element, there is no heat of formation, so the heat of formation here is 0. For carbon dioxide, we look up the value to be negative 393.5 kilojoules. But we have to multiply this number by 8 because in our balanced equation we have 8 moles of carbon dioxide. And the heat of formation for gaseous water is negative 241.8 kilojoules. And we have to multiply by 10 because there are 10 moles of water in the balanced equation. When you're looking up the heat of formation for water, be careful to determine whether or not you're looking up the heat of formation for gas or the heat of formation for liquid water. There will be a difference because it will take energy to heat the water from a liquid state to a gaseous state. The next thing we do is to add up all the heat of formation for the product side, the reactant side. 2 times negative 125.7 is negative 251.4 kilojoules, and the sum of all the heat of formation of all the products is negative 3148 kilojoules plus negative 2418, which equals to negative 5566 kilojoules. Now we're ready to use our shortcut equation. The heat of formation of all our products is negative 5566 kilojoules minus the heat of formation for all our reactants, which we determined to be negative 251.4 kilojoules. We add it all up. The enthalpy for our reaction is negative 5,314.6 kilojoules. However, we want to find it for the molar heat of combustion for butane, and because we used 2 moles of butane, we have to divide our final answer by 2 to get negative 2,657.3 kilojoules per mole of butane. Let's use the information that we've just learned to solve a multi-step problem. Our example here is, what mass of methanol fuel must be burned to heat 752 grams of oil with a specific heat capacity of 3.62 kilojoules per kilogram degrees Celsius in a fondue from 21.6 degrees to 224.8 degrees Celsius. From our work in calorimetry, we know that the change in enthalpy for a reaction will be the quantity of heat absorbed or released into environment. The enthalpy change for a reaction we know is the number of moles multiplied by the molar enthalpy of our combustion equals Q. Q we can substitute with mc delta T. We must find what mass of methanol. Mass is really just another term for N. So we're really looking for N in this case. We have a mass. This mass here is for the oil that is being heated in a fondue. We know the specific heat capacity of the oil is 3.62 kilojoules per kilogram degree Celsius. And here the temperature change we need to find is approximately 200 degrees. So we have everything we need to solve for N except for the molar enthalpy of combustion. And this is where Hess's law will be coming into handy. In order to find the molar enthalpy of combustion for a reaction, the first thing we need to do, of course, is to have a balanced equation. So here we have 1 mole of methanol reacting with 3.5 moles of oxygen gas to produce 1 mole of carbon dioxide and 2 moles of gaseous water. After we've determined the balanced equation, the next thing we need to do is to calculate the molar enthalpy of combustion. To do that, we need to look up the molar enthalpy of formation for methanol, which is negative 239.2 kilojoules. Remember, oxygen is an element, therefore it has no enthalpy of formation, so it's 0. The enthalpy of formation for carbon dioxide is negative 393.5 kilojoules, and for gaseous water is negative 241.8. However, remember to multiply this number by 2 because the coefficient for water in our balanced equation is 2. So we add up all the enthalpy of formation of our reactants and is negative 239.2 kilojoules. For our products, it is negative 877.1 kilojoules. Using our shortcut equation now, negative 877.1 kilojoules minus negative 239.2 kilojoules. The answer here is negative 637.9 kilojoules. This is for one equation. However, we can easily convert that to per moles of methanol because there is only 1 mole of methanol in each equation. So we've just determined the molar enthalpy of combustion for methanol to be negative 637.9 kilojoules. We can now take this value and bring it back to our calorimetry equation to solve for N, which we'll do on the next slide. And finally, now we can solve for the mass of the methanol because we've just calculated the molar enthalpy of combustion for the methanol. Again, on the left-hand side, we'll set up our calorimetry. The change in enthalpy will be equal to the amount of heat absorbed by the water, or in this case, the oil. We have N times the enthalpy of combustion. We've just calculated the enthalpy of combustion to be 637.9 kilojoules. On the right-hand side, we have mc delta T. All of these values were given to us in our question. The only thing we weren't given is to find the moles. And remember, when we're given a mass, we can find moles by dividing by the molar mass. So instead of writing N, we could substitute in little m, which represents mass, divided by big M, which is molar mass. And you can calculate the molar mass of methanol by simply adding up all the atomic weights of the atoms in methanol. So now we have our final equation. We can solve this in one step, although if you like, you can solve it in 2 steps as well. We calculate that our mass is 0.0278 kilograms, or 27.8 kilograms. So 27.8 grams of methanol is required to convert 0.752 kilograms of oil from 21.6 degrees to 224.8 degrees. I hope you find this shortcut method helpful in determining the enthalpy of reactions using Hess's law.